Where?
In Indianapolis,
Oh, okay. I thought you said India.
Indiana.
Yeah. That'd be quite a ways out.
Yeah.
So you're somewhat of a scientist.
Yes.
Just
Well, I studied physics. I was started out actually in electrical engineering. My father was an electrical engineer, but I got a bachelor's degree in electrical engineering from Columbia University. But I switched to physics when at the time the laser was young, and I wanted to work with some high power physics. So with lasers, so I was able to write a doctoral thesis on that subject. It was based on work I was doing for a private research company that had government contracts. And the beauty of it was that the contract with the government paid for the research, and then I just changed the cover of the first scientific report, and it was my doctoral thesis.
wow. So it's top-notch, front of the line science.
It did make Physical Review, which is the most prestigious physical journal, and it got in there the first time out of the box, so I guess it was sufficient quality for them for New York University to give me my degree.
Wow, sounds pretty good. And so Columbia is a top-notch university as well, and lasers, was that a passion of yours, or?
Well, let's see. I've always been interested in light, and then, at the time in 1964 when I graduated, the laser had only existed for 4 years. So it was a chance to get in on the ground floor of some new science. When I did my research for the doctoral dissertation, I only had to look back about 6 years by the time I had finished the thing, because there just wasn't any history of high-powered lasers before then.
Wow. Were you one of the first then to work with high-power lasers, or?
I was one. We were one of the first. The research department I was in had a contract to study how lasers damage themselves or damage high-power glass materials. The high power of the laser would actually cause damage in the glass, just going through the glass. Let's see, a low-power light just goes through the glass, but when the power is greater than a certain amount, it provokes a reaction in the glass. It sets up a sound wave. The sound wave focuses the light. It's more focused in a thinner beam, so the reaction is more intense, and the whole effect runs away until the laser beam is down to about a wavelength of light in diameter, but it can go on for centimeters if the glass is long enough. And this phenomenon had never been observed before there were high-power lasers. So I did a theoretical analysis which took a sound wave and took a light wave and figured out the interaction between them. And there were a number of other people who were trying to analyze this, but mine was first and went farther than others had done. So
the interaction between sound and light?
That's right. And it was new physics essentially because of new technology. Physics had never been able to observe this before there were high-power lasers.
Because in the laser there's something between sound and light.
Because
they affect each other? Because
the light sources they had before might have been more intense than the laser, but they couldn't be focused as the laser could be focused into a tight beam. So therefore they had never seen a beam that was so intense, had so much power concentrated in it, and therefore all sorts of new things happened that nobody had observed before. Another analysis was due to not sound and light, but what they called Kerr effect. It wasn't, however, named after me. It was named after a Scottish physicist in Edinburgh. His name was John Kerr. I also had a forebear, a great-grandfather named John Kerr about the same time, but my John Kerr lived in Ireland, and the other one, so, you know, it was just the coincidence of the name. I did not analyze Kerr effect. I analyzed the sound and light distribution, and then other people analyzed the Kerr effect and so forth. So I was able to show that the damage caused in glass was, at that time, was being done by the sound wave and not by the Kerr effect. But the Kerr effect was important when lasers went through liquids.
Okay.
They would leave a trail of ashes behind, which would settle down from where the beam had gone through.
Wow. That's impressive for a beam of light.
Yeah, right. So I did get in on a lot of interesting research when I first started out at after graduation from Columbia University in electrical engineering. But actually, one of the first projects I worked on was how to use a laser beam to send signals back from Mars to make real-time television possible from Mars. You know, they have a space probe, say, looking at the ground, you know, and the scenery flying by very fast, and being able to see that in real time on the Earth, using a laser beam to report the data instead of radio waves.
So that would replace what they use, for example, for the Explorer type.
Yes.
Are they satellites?
Yeah, right. The space probes still use radio rather than lasers to report back to Earth. I know that
They report further than Pluto now, don't they?
they would have to, and the farther they go, the weaker the radio gets because it spreads out. You can't focus the radio beam smaller than, say, the diameter of the Earth's orbit, but you could focus a laser beam as small as the diameter of the Earth. So therefore you can concentrate the energy from the space probe and therefore get the data back much faster.
So you can have a communicating laser, not a destructive laser?
Yeah, right. Yeah, I know that the Star Wars ideas, of course, the destructive lasers. When I first did my research, they would measure the power of a laser in gillettes. That is, if it could burn through one razor blade, then that was a 1 Gillette razor, and if it could burn through 2 at once, that was a 2 Gillette laser.
I was actually going to say, is that the razor? But you beat me to it. That is pretty funny.
Yeah, right. Anyway, they gradually got bigger in power, and about the time that the Air Force Weapons Laboratory was actually looking at lasers that might burn down missiles about that
Like
time.
the YAL-1,
Yeah.
that Boeing plane with a big laser on the front.
Yeah, well, right, that was one of the ideas that was being used. The idea is that a missile cannot go faster than the speed of light because it's a material object, and therefore it could not outrun a laser beam. So that would be the ultimate anti-missile. This idea does not work very well because the atmosphere would eventually absorb some of the laser beam. The gas in the atmosphere would get heated up where the beam energy was absorbed, and that would form a lens which would diverge the beam. And if the beam is no longer focused but it's diverged, then
It doesn't have
the
that
power
destructive.
is spread out, yeah,
I
so
see.
it wouldn't be effective at burning down missiles. And they do have anti-missile missiles, but they don't use lasers in them.
Good to know.
Mhm.
Not that I'm
Yeah.
planning on, destroying any missiles soon. But
Right, yeah, and I'm not giving away any military secrets because the Russians know this too, so.
yeah. But so the idea was to be able to have live TV from Mars
Yeah.
or anywhere, and like our galaxy, pretty much, or?
Well, by extension, of course, once you solve the problem of TV from Mars, you would want to be able to take it to, you know, planets farther out. But we have to get there first, you know. My generation got to the moon, so.
So did you ever figure that problem out, like solve
Yeah,
the?
I wrote with some other colleagues, we wrote a very thick report on all the experiments you'd have to do and the analysis, the power requirements and so forth for real-time TV. And we wrote a report that thick, and NASA thought, well, this is wonderful. We never get a report this thick on such a small contract. But they said, oh, we're going to put this in all the libraries in the world and all that. And so I went on to other projects and forgot about it. But 20 years later, I had an opportunity to work directly for NASA at the Jet Propulsion Lab. And while I was there, also working on laser communication, I decided to look up and see what happened to our old report. And you know what they had done in the previous 20 years?
Absolutely not, but.
You got it, absolutely nothing, and done any of it.
Wow.
So in our department, which was in charge of, you know, laser communication, lasers in space, in deep space beyond the orbit of the moon, I worked there for several years. Then I decided to go to Spain, which I'll tell you about in a minute, but I told them at the time that if I would be gone, but if they didn't do anything more in the next 20 years, I would come back to haunt them.
So,
But it
have you
turned
done that?
Well, it turned out that the second time was more successful. They asked me to design a laser to use on Mars. This was it was an orbiter, a space probe orbiting Mars. And the idea was they would bounce a laser off the surface of Mars and measure the time from the emission of the pulse down to when it's reflected and then it came back. And since they knew the distance to the center of Mars and they knew the position of the spacecraft, then the time would give them the height of the mountains and the depth of the valleys.
That makes sense, I suppose.
Yeah.
Did it work?
Yes, it worked very well. As a matter of fact, because they used that design, we now know the topography of Mars better than we know the topography of the Earth.
That's kind of sad.
That seems sad, right, yeah. Well, you see, it turned out that radar was used very well on Venus. Venus is always covered with clouds, and the radar penetrates the clouds.
Where the laser doesn't.
Where the laser doesn't. And so they made, you know, beautiful maps of the surface of Venus through the cloud layer. Mars very seldom has clouds. It has dust storms occasionally, but the atmosphere is very thin. And the thing is that radar would also penetrate the ground, especially because the ground is sandy and dry. It would, as a matter of fact, penetrate an unknown surface to an unknown depth. And this, well, you don't know the characteristics of the surface, so you don't know how far down before the radar wave starts coming back. So since they want to plan landing on Mars like
They have to know what the ground's made of and how high up it is.
how high up it is, you know, because you could, with the radar, you might be off by as much as 30 feet. You know, you thought you had come down to the surface,
Yeah,
and then it was a 30-foot drop still to go, you know.
I was thinking being off by 1 foot would be bad enough. If you're trying to send something a foot underground, you might
Yeah.
crash it.
Yeah, right, but no, it was worse than that. It was about 30 feet with radar. But the laser is reflected from the top millimeter, and therefore they know the distance to the ground within, you know, less than an inch, you know, within a centimeter. So
Sounds extremely accurate.
yeah, it was. It was very successful, and they liked it so well. They also sent another one to the planet, to the asteroid Eros. This was just to photograph the asteroid They would, of course, like to land on it and explore the surface, but they never expected they would be able to do that until they designed another probe. So they sent out a probe there with no landing gear or anything. It was just going to fly around it. Did have the laser, and they were able to measure the surface so well that at the end of the probe's life, when everything was nearly worn out, they decided to risk trying to land on it, even though there's no landing
I
gear.
remember hearing about that.
Yeah, and so they just, matched the speed very exactly, and they knew just where the surface was, and they set the probe down so gently that there was no damage at all, and it continued to send signals from the surface of the asteroid. So they got, surface exploration where they had expected only an orbiting mission.
That was thanks to lasers and your
To the
research
laser.
and your team and all that. That's pretty cool.
Yeah. And then there is a laser now being used on a mission to Mercury. It's in the Messenger satellite. It's also mapping the surface of Mercury. And the Japanese Space Agency made their own copy of the laser altimeter, and they put it on the Hayabusa probe, and they went to the asteroid Itokawa, and they actually returned a sample from the surface of the...
Wow, so not only did they land, but they brought it back.
Yeah, they didn't actually land. They blew it off with another laser, a more powerful laser, and then they captured it. So.
Oh, that's cool.
But anyway, that had to be, they had to be close without landing, and that's just as hard.
Wow. A lot of interesting stuff going on in space exploration.
Yeah. So I've had fun doing this. Actually, when I was a student engineer, my father was working at Cape Kennedy with the high-intensity lighting of the space launches so that they could launch at night if that turned out to be convenient. And I spent one summer on an instrument that lines up the spacecraft just prior to launch, so that when it has been launched and after the first few minutes it's spent most of its fuel, but it's headed for the moon, that it would be on course. If they were to launch it toward the moon and then discover that they needed to make a mid-course correction, there wouldn't be enough fuel. They would either get too close to the moon and so make too tight a turn around it, or else they'd go too far from the moon and not make a tight enough turn around it, and they would go off into space. They wouldn't have enough fuel to correct their course and return to the Earth. So they would just be going off farther and farther from the moon and the Earth until their oxygen ran out.
Sounds drastically bad.
It was drastically bad, and therefore they spent quite a bit of money getting an instrument ready that lined up the space probes. It transferred the last coordinate 17 seconds prior to launch. And if they aborted the launch, say after only 5 seconds into the remaining in the countdown, they would have to go back to several minutes, about 5 minutes before, reset the countdown to 5 minutes before, so as to get everything set again for the next attempt at launch.
Because of the movements of the moon and the Earth and everything, is that?
That's right, yeah, the Earth
Okay.
is always rotating, so they had to transfer the coordinates at a certain known time and compensate for the slight motion after the coordinates were transferred. So the instrument must have worked because the astronauts all got to the moon.
Yeah.